Hello everyone, welcome to this presentation. My name is Shupeng Zhu. I'm a senior research scientist from the Advanced Power and Energy Program at UC Irvine. Here I'm going to talk about a collective research effort made for qualifying the economic footprint of California wildfires in 2018. Our research partners come from two elite universities in China and two top universities in the UK. Wildfire has long been a major threat to lives in California. As we can see in this figure, such a threat is growing over the last decades, and it has reached a new high this year. The increasing drought and rising temperature due to climate change is considered one of the main causes of such a trend. Other causes, including lightning, increasing human activities, and aging grids. Before this year's devastating wildfire, those happening in 2018 is considered the most deadly and causative fire disaster in California's recent history. That's why we focused our study on wildfires incidents in 2018. This map here shows the location and magnitude of the major wildfires in 2018. Among them, the Camp Fire starts on November 8 is one of the most deadly and destructive fires in state's history, which wiped out the entire town of Paradise and claimed 85 lives. So, what is the economic footprint of wildfire? Usually, when considering damages caused by wildfire, people only look at direct damages, such as structure destruction, infrastructure damage, and casualties. Although those statistics are most straightforward and prevalent, they have only tell part of the story. Wildfire can cause some significant indirect damages, such as health damage caused by wildfire-induced air pollution, economic damage due to transportation and labor supply interruptions, also upstream and downstream supply chain impacts. By bringing together all those damages, the economic footprint provides a more comprehensive understanding of how wildfire could impact our society. This sketch here shows our methodology in brief. First, the productive capital loss resulting in loss in production capacity is calculated. Then the traffic distribution, which contributes to transportation constraints and provides productive time loss. Moreover, the wildfire-induced air pollution results in health degradation and activity avoidance, which also contribute to productive time loss. Finally, the impact on the supply chain results in behavior changes in product strategy and market demand. Altogether, we construct the demand-driven production constraint for the calculation of economic footprint. Here's our model framework, which contains 5 different parts. First, the measurement data from the AQS² observation network are merged with satellite data from the MODIS project, using a random forest model to generate the daily ground level PM2.5 concentration map with 1 km resolution. Other data simulations from meteorology and air quality are also used in this process. Here we got a reference PM2.5 concentration, CS. To separate PM2.5 that is caused by the wildfire, 2 air quality simulations are conducted using geoscam, with one scenario accounting the wildfire's emission and one without. We can calculate the ratio of wildfire contribution. Now we can use the ratio to compute the real wildfire-induced PM2.5 concentration, the delta C, from the observation dataset. Then the bandmap is used to calculate the health and economic impact related to wildfire air pollution. At the same time, the direct capital loss is evaluated based on the official report on destroyed asset and the rebuild cost evaluation obtained from different insurance companies. Finally, a multi-regional disaster footprint model is used to calculate the indirect loss. Since most of the devastating wildfire happened in the late half of 2018, here we showed air pollution status between July and December. Here, October and December provide a reference for the annual normal air quality status without much of wildfire. In general, most fires in 2018 started in July and June, and expanded in August, and we can see the North California and Sierra Nevada region are most impacted. At the worst, unhealthy air quality covers over 31% of states' acreage in July 13. While the air quality back to normal in early September, as most wildfire previous burn has ended, except for that fire. However, the wildfire came back in November, including the deadly campfire, while this time it has impacted more populated region. In November 17, unhealthy or worse air quality affects more than 39% of state's population. Here we calculate the health cost related to fire smoke using BMAP. The estimation is for premature deaths is over 3,600, which is much higher than the direct fatalities. Those premature deaths caused a loss of $27 billion for the value of statistical life. This figure here shows the relative cost due to mortality and different mobility endpoints. Here we can see the cost of mortality really stands out compared to other endpoints, while for mobility, the acute miracle infection and work lost day are most costive endpoint. Here, the total cost of medical expense is estimated to be 210 million, and while the cost due to work time loss is about 130 million. These two figures shows the distribution of those costs in total and per person. For per person cost, this distribution is more cost close to the air pollution location. However, the total cost distribution is more related to population densities. So more cost is attributed to the South Coast region and the Bay Areas. This figure here shows the direct capital loss for some of the top 10 fires and split it into household damage and productive damage. We can see in general there's more damage to the productive capital than for the household one. In total, the direct capital loss reaches 27.7 billion, which is smaller than the house cost. Although its burning acreage are not the biggest, the campfire attribute to more than half of the local capital loss, followed by the Woolsey fire and the Cali fire. The Mendocino complex fire ranks only number 4 in the direct capital loss, although it has the largest burned acreage. For the geographical distribution, we find heavy total loss in the SoCal region and the North California, while for per person loss, it is more concentrated in the North California. Here we summarize the indirect loss, which is also the largest among all losses. It accounts for the loss due to the disruption of productivities and the supply chain. Not only in California, but also for the entire U.S. The total loss in the U.S. reaches 88 billion, which equals to 0.4 of the annual GDP of the country. More than half of the losses are from outside of California. As for the geographic distribution, Sacramento has the largest total loss in the absolute number. However, the Butte County has largest loss when compared with its economy. Its indirect loss equals almost half of its annual GDP, which reveals the level of devastation in that region. Also, Butte County was singled out in both the total loss and the per person loss. Here, we summarize the economic footprint from all 3 types of losses. This plot here shows the distribution among different types of losses for the top 29 counties with largest losses. We can see different counties has very distinct distributions. For the Butte County, most of its loss losses are from capital loss, while most of other counties are suffering from health and indirect loss. Only Los Angeles County has rather equal distribution among those three. The total damage reaches over 184 billion, which is roughly the 1.5% of California's annual GDP. Among all three factors, the indirect loss only accounts for 90%, while the indirect accounts for more than 50%. Moreover, 31% of total loss were outside of California. The top three counties in total wildfire economy footprint are Butte County, Sacramento, and Los Angeles. In general, we find per capita losses highlight areas where relatively low population but with larger losses, like the Butte County. Here we show the distribution of the top seven sectors with the largest economic footprint. As we can see here, the surface sector has the largest losses. It is rather balanced between those three different types of losses, although slightly towards the health and capital loss. Within the surface sector, we can further decipher it into dozens of subsectors, all have different loss compositions. The real estate sector has the largest loss and is most composed of direct capital loss, while the health sector is more impacted by the health cost. Then we have the manufacturer as the second largest loss, where most of the loss are indirect loss. Within this sector, chemical industry, which is also the largest manufacturing sector in California, suffers most losses. The trade sector ranks third from the total losses, with almost equal distribution from three different types of loss. Within this sector, wholesale and non-store suffers the biggest losses. Finally, here's our conclusion. In this work, we have proposed a comprehensive assessment framework of socio-economic externalities of wildfires. Accurate assessment of those externalities of wildfires is crucial to the design and evaluation of wildfire prevention policies. For a larger perspective, it is also enriching our understanding of the dangers imposed by climate change. Also, within this framework, we explore three aspects of wildfire losses. For those incidents happened in 2018 in California. As the most adopted factor, first, we find out that direct capital loss reaches 27.7 billion, which is about 0.8 of the state's annual GDP. However, fire related to health cost, which is really estimated, turn out to be much higher than the direct capital loss. Finally, in the first time, we estimated the indirect supply chain loss due to wildfire, and it shows an astonishing figure of 42.7 billion within California, which is also twice of the direct capital losses. There are even more indirect losses due to supply chain beyond California. We also find uneven spatial and sectoral distribution of those losses, which indicates that different policies focus should be considered for different sectors in preventing or evaluating wildfire risks. Thank you very much for your attention, and I'm looking forward to hear your questions. Thank you.